Okay, now continuing the discussion on indexes, let's take a look at the actual data structures used to implement them. The basic goals of an index and any collection data structure really are we want to be able to quickly add things to it, remove things from it, and search for things in it. So that's not unique to a database, but we don't just want an index to support searching. We need to be able to quickly modify them by adding or removing rows. And for searching, I specifically list two kinds here. We want to be able to do range queries, and by that I mean find all things in between a range. So say like everything in between two dates or everything after a certain date. And then just exact matches. So find the one row that has exactly X for a certain column. So we want it to quickly support all of these things. So think back to your algorithms and data structures class, like 2420. And the most basic data structure that will support all of these things that probably everyone is familiar with would be a binary search tree. So I list BST and hash table here. Let's take a look at the difference. So the first two, insertion and deletion, will be efficiently supported by BSTs and hash tables. Hash tables will be a little faster there, actually. But then for the searching, a BST is the only one between these two options that's going to support range queries. A hash table just can't do that. There is another concern specific to databases, though, and that is that we're dealing with massive amounts of data. So even though these indexes are just auxiliary structures that help us quickly find the full row, the full data, there's so much data that even the index can be very large and may not reside entirely in memory at once. So while we're performing these operations, insertions and searches and so forth, we need to bring part of the data structure into memory at a time, which means we need to go out to disk possibly multiple times while traversing through this tree. So the fourth criteria on an index structure is we should touch as few disk pages as possible during these operations, insertions, deletions, and searches. So we'll use a binary search tree as a starting point because it has good algorithmic complexity for the operations we want, but then we'll look at optimizing it for reducing the number of page accesses when the data is so large that it resides on disk. And we'll end up with not a BST, but a different kind of search tree that's designed specifically with disk pages in mind. So if we use a BST, an index would look like this. We have the full table containing every column and every row, and then we have the tree containing just the values from the column or columns that we want to build an index on. And those values are what determine the shape or structure of the tree that lets us quickly search by that value. So this index was built on just the class number column. And so the values in those nodes are the values from that column. And those values are called index keys. But it's important not to confuse that with relational model keys. This term keys does not mean uniqueness like it does in the relational model. Those are just the search keys that decide the structure of the tree and let us quickly search through the tree. So in addition to these search keys, the tree also has pointers into the full row. So once we've found a particular class number, we can go and find the full row for everything, all the other information about that class. And then we could have another index built on the name column or some other column. So we can have this big mess of pointers coming into the main table, and any given row in the main table might have lots of pointers coming into it, so that we can find that row from different search criteria. Remember though, these indexes themselves are possibly very large and have to reside on disk and are spanning possibly many disk pages. So when we're constructing this tree, how do we decide where to allocate new nodes? If you're writing a tree just in a programming language that's going to live in memory, you just call new, and that's how you decide where the new node goes. The memory allocator just puts it somewhere for you. But if we're building this tree on the disk, we have to decide where on the disk to put new nodes. So the simplest option is we'll just keep track of the current page that we're dealing with, And as we are adding new nodes, we'll just put them onto the end of that page until the page gets full. Once it gets full, we ask for a new page from the disk and start putting new nodes in there. And then we just have to make sure all the pointers are going to the right places, so there may be pointers going all over the place in terms of pages. So let's visually illustrate this just to see how this would work. Let's say, as an example, that a page can hold 3 nodes of a BST. And that's just to make the example reasonable. So pretend that these nodes are really large, or maybe pages are really small. And then we're going to insert these items in that order into an empty BST. And then we'll see what the structure of the tree looks like in terms of how the nodes span across different disk pages. So we'll start by inserting I. So since it's the first one, we just make a new root node and put I in it. But that node needs to go on the disk somewhere. So we get a new page from disk, and we will say that the current page is this light blue region. So I goes into the light blue disk page. Okay, we insert J now. It can fit into the same light blue page, and structurally it just goes to the right of I due to the BST structure. If we insert D, it looks like this, and the whole thing currently fits in one page since it's only 3 nodes. But as soon as we add another one, that's at the capacity of this page, so we'll have to get a new page. So if we insert B, our current page will now be this red page. So we have 2 total pages now, and structurally B goes to the left of D in the tree, which just means this is a pointer to somewhere else on the disk. The fact that this is not really a memory pointer but a disk pointer makes no difference. It's just a number representing where something is. Okay, so if we keep going, we add F. It now looks like this. So we have a couple pointers coming out of D going to a different page on the disk, and B and F live in the same disk page. We add A next, so the tree looks like this, and A, B, and F are all on the same page. Now that page is full, so when we add H, we need to get a new one. So green is now our current page, and structurally it's going to go to the right of the F node. Okay, we keep going, we add an E, it looks like this. Keep going, we add C, it looks like that. So now we can see that we can have pointers coming out of various different parts of the tree going into different disk pages. And it's all purely just based on the order in which nodes were added, and thus the order in which pages fill up. Okay, if we keep going, we add G, and that's the last item we're going to add. So we have this last page here. It's only going to have one thing in it, though. Okay, so here's our tree, and it's spanning 4 different disk pages. Now let's look at what happens when we try to search for something in this tree. So let's say we're searching for G, that bottommost leaf node. Okay, so we just follow normal BST traversal algorithm. So we start at the root node, and I'm going to track, while we're traversing this algorithm, I'm going to track which pages we have visited. So to get to the root node, we have to load the light blue page. Okay, we're going to go to the left and visit the D. It's in the same page, so we've still only visited the light blue page. And we go to the right, so we have to pull in the red page containing F. Notice, though, we just pulled in the entire red page, including A and B, even though A and B are clearly not going to be involved in this search, because we're going to go to the right next. So we go to the right and we pull in the green page, and then we go to the left and we pull in the yellow page. So a couple of things happened here. When we visited node F, we pulled in the entire red page just for that one node. When we visited node H, we pulled in the entire green page just for that one node, and then immediately just skipped out of that page. So we're not getting very good reuse of pages. Once we pull in a lot of information, we're essentially just throwing away most of it. We didn't really do anything with that. So there are a couple of problems going on here. One is this tree is not balanced, so it's not a self-balancing BST. And more importantly, though, the tree is not organized with page reuse in mind. Ideally, if we wanted to search for G, the pages would be organized kind of like this. So if we can fit 3 nodes per page, then we would have one page containing those 3 nodes so that we could visit I, D, and F all in one page. And then we would have another page containing those 2 nodes, at least those 2 plus maybe another, so that we could then visit H and G. And we could get all the way down through the path through our tree with only visiting 2 nodes, 2 pages instead of 4 pages. But how could we predict that G is what we wanted to search for? How could we predict that this was going to be our path through the tree? And we can't really. Like, what if we suddenly wanted to search for a different node like A? Then we would need a different page structure. But we can't predict what kinds of searches we're going to do, so we can't predict how to organize these pages. We're going to have to do something else. Just to kind of summarize this problem, though, let's look at these red and green pages. We loaded those full pages just to get one node out of them, and then we immediately just skipped out and went to a different page. So we visited 5 total nodes, I, D, F, H, and G, and we had to load 4 pages in order to visit those nodes. So almost one page per node. Ideally, since we can fit 3 nodes per page, then the best we could do is load 2 pages to get to the bottom of this tree, or to get to G. So that's what we'll have to try to do. So let's try to address this first problem. The tree is not balanced. So, well, we can easily just use a self-balancing BST such as an AVL tree. And if we did the same insertion order of these items, we would get this tree. So it is more balanced. The height of the tree is reduced. G is not kind of out there on its own level. But we haven't done anything about how the nodes are organized within pages. So they're all still kind of just scrambled across pages. And if we were searching for G, we would still have to load the blue page, the green page, the red one, and the yellow one. So it's just as bad. We have visited fewer nodes, only D, H, F, and G, but visiting fewer nodes is going to make very little difference. Remember, the biggest impact on performance here is how many pages are loaded, and we're still loading 4 pages, so this is essentially no better. And in the next video, we'll look at how to rearrange the tree so that we get more reuse out of each page.